Nelson, and thanks for having me. It's a pleasure to be here. So my focus today and also on Monday morning will be on the cosmological sources of gravitational waves. And you've heard a lot about sources of gravitational waves, most of them focusing on either neutron stars or black holes or some combination of them. So what I'll try to do here is focus more on the early universe and gravitational waves that we expect were produced then. And in fact, if you go through the literature, there is dozens of different models that have been proposed, and they have to do with inflation. So I know most of these terms are might not be familiar to you, but as we go, I'll try to introduce what we need so that we can all kind of follow. So inflation, this is a period of a rapid expansion very early in the universe. We'll say more about that. There is a standard model, which I will focus on the most today and on Monday, which has to do with what is called the amplification of vacuum modes. But then there are also numerous variations on this model, and they have to do with different kinds of physics as well, and I'll touch on some of them. Phase transitions, this is as the universe started off hot and cooling down, it went from one phase to another, and when that happens, you could have certain transition processes that take place, and those can also generate gravitational waves in different ways. Cosmic strings are potentially a leftover of these phase transitions, or potentially they could be fundamental strings, like string theory strings. And they could be colliding, having cusps, kinks, and so on, and producing gravitational waves in the process. There is also a lot of uncertainty in what happened in the early universe, so there could be additional things that went on, additional physics at very high energies that we don't know of. So that could potentially change what we expect happen in terms of gravitational wave production. There are also exotic models like alternative cosmologies and so on, and I really won't say much about them. The common thing about all of them, though, is that there is no predictable waveform. In all of these situations, you have many things going on simultaneously, not in some correlated or coherent way. So you can imagine it just basically being the same as billions of binary neutron stars colliding all across the universe and creating this kind of a humming noise in the background. We call that the stochastic gravitational wave background, and you heard from Joe yesterday, and I guess after me he'll continue. He already introduced the concept of the stochastic gravitational wave background, so we'll build on what he said, and I will focus mostly on this standard inflationary model. So I'll try to give you a flavor of what that's about and why that's important. In many ways, this is, depending who you ask, some people may say this will be the holy grail of our field. If you can detect this, you're looking at the universe right at its beginning. After we're done with that, then I'll summarize a variety of these other models that I mentioned and their detectability. So in terms of the sources, here's some list of really useful ones, I think Joe mentioned this one already yesterday. These are lectures from Bruce Allen from, boy, is that 22 years ago? So Joe said that he learned from this about the stochastic background. So did I, and I can tell you everybody in my group did too. So this is really a star piece of text if you want to learn about this. Then Michele Maggiore has a very long review, about 100 pages, that we also used when we were starting. And there is a more recent review by Chiara Caprini and Daniel Figueroa that came out this year. This is in some ways our Bible. So Bruce Allen and Joe Romano, they published basically or define really how to search for stochastic background. So what we do in LIGO and Virgo searches is basically what's in this paper. And then there are some books that you can also look into. So Michele Maggiore has a book that deals with a variety of sources, and I think a lot of what's in here is in here. and Jolyon Creighton and Warren Anderson also have a very useful text, also a textbook that I find really pedagogical as well. So I would start with these. Of course, there's a lot of other things that you can find in the literature, but I think these are good starts. So just so I have some sense, how many of you have studied cosmology before? Okay, so a fair fraction, not everybody. So we won't need a huge amount of cosmology here, fortunately. So I will spend about 2 slides kind of introducing the relevant concepts, and then we'll assume you know everything you need to know. As probably everybody knows, the universe, we believe, started as in some event that we call Big Bang. So it was very, very hot initially and started to expand and cool off over time. And as it was cooling, as it was expanding and cooling, different parts of physics were becoming relevant. Okay, so physics at different energy scales. So initially, we think there is some evidence, although nothing that you could consider proof, that we believe there was a process of very rapid expansion, which we called inflation, and this happened at very, very high energy scales. So this is, I don't know if you can see, but this is 10 to the 32 degrees, or in the particle units, this would be something like 10 to the 19 GeV. And then it started to cool off. After that process, after the inflation, basically we believe all of the regular particles were generated. And initially you can imagine this as being a soup of quarks and gluons and leptons and so on. And as the universe cooled, you would go through this process of baryogenesis, where you create protons and neutrons and so on. And then somewhere here, those protons and neutrons start to basically form nucleons, the lightest nuclei, basically things like helium, deuterium, and so on. That happened about a minute or so after the Big Bang, and at that time the temperature was at about an MeV. So the processes, basically the beta decay related processes that were initially converting protons to neutrons and back, they froze out because the rate of those at that temperature basically became smaller than the expansion rate of the universe. So when that happens, the protons and neutrons essentially became decoupled, and they started to form the nucleons. This is where you form these lightest nuclei. And then after that, at that point, they're still ions, so they're not neutral atoms. They're ions because photons that have MeV energy can easily knock out electrons from the atoms, right? You remember the 13.6 eV in the hydrogen atom. So it took about 380,000 years for the temperature to drop to something like an sub-eV, at which point the number of photons that had enough energy to ionize the atoms was small enough that these atoms could remain neutral. And at that point, the photons actually decoupled from the rest of this plasma, from protons and electrons and so on, and they started to basically freely travel, and they reach us eventually, and that's what we call the cosmic microwave background today. After the photons decouple, the rest of the stuff, so atoms, hydrogen, helium, and so on, they start to fall into the gravitational, they're falling in towards each other under the influence of gravity, and they start to form stars, galaxies, and the structure we observe today. And that's basically the process that takes the remaining 14 billion years. So that's in a nutshell the history of the universe. The important thing for us here is that when we were over here, this is basically the quantum world, and this is where we have quantum oscillations. So fluctuations, if you like, in the vacuum. These fluctuations persist throughout, and they eventually become seeds for growing the galaxies and clusters of galaxies, basically the structure we observe today. And there were also the seeds, or a reflection of them, if you like, you can see in the cosmic microwave background as well. So our our job today and on Monday basically will be to talk about this stuff. What happened here in this region before the universe was about a minute old. We have pretty good idea what happens here. This is what regular astronomy tells us. We have excellent idea of what happens when the photons decoupled. The CMB experiments have given us that. We also have a pretty good idea what happens with the Big Bang nucleosynthesis because we have measurements of how much helium and deuterium and so on there is in the universe, and it matches the nuclear theory. But essentially before this 1 minute, we have no experimental data. And this is where the physics of very high energies would come in. There are a variety of processes that we expect should have happened or could have happened, and many of them could be producing gravitational waves. So we'll talk about that. I'll mention a couple of things here. One is that after the inflation is done, the energy of the particles is very high, and they're all basically considered relativistic. So the phase of the universe that follows right after the inflation is typically called the radiation domination, because all of the particles effectively are relativistic. At some point somewhere here, the temperature is low enough that you start to have non-relativistic particles, and that phase essentially is dubbed the matter domination. So there are these phases in the universe, known phases in the universe, that we'll talk a lot about, and they have a lot to do with the kind of gravitational wave background that we observe today, or that we hope to observe today. All right, so the expansion of the universe quantitatively is described by the Freedman equation, which is given here. And this is an equation that basically comes out of Einstein's equation under some assumptions. Basically, you assume that the universe is isotropic and homogeneous, so it looks the same everywhere in all directions. And under such assumptions, you can figure out what the relevant metric should be, and then you're led to an equation that looks like this. So the A here, and we'll talk more about that as we go. The A is what we call the scale factor. This basically tells us how large the universe is at any given time. So it captures the size and the evolution of the size over time. If you take A dot, so the derivative relative to time of this scale factor, and you divide it by A itself, we call that the Hubble parameter H. And we'll be talking about that a lot as well. So on the right-hand side, there are a couple of interesting things. So these are constant. G is just the Newton's constant. Rho is the energy density in the universe. And the K here captures the geometry of the universe. And for our purposes here, we'll assume that K is equal to 0, meaning that the universe is flat. So forget about K. Really what we have is that the scale factor time dependence is related to the energy density in the universe. So then you can go back and ask, well, what does the energy density look like? How does it behave? How does it depend on the scale factor? And that changes in these different phases of the universe. So remember, we had the radiation domination, matter domination, inflation as well. So these are the three phases that we will be playing with. In the matter domination, the energy density as the universe expands by a factor of 2, the energy density will drop by a cubic factor of that, right? So it will scale as a to the power minus 3. So if you put a to the minus 3 here, there's another a squared that goes to the other side. Then you have a simple, relatively speaking, simple differential equation in A, and you can solve it, and you find that A scales with the time to the power 2/3. So the universe expands in the matter domination. And radiation domination, well, in this case, the scale, the energy density scales with the 4th power of A. 3 of them are coming from the same reason, right? The universe just expands, so the volume is bigger. The last one comes from the fact that as the universe expands, the wavelengths expand as well, so frequency drops, and we know that the energy of these will be just h nu. So if nu goes down by a factor of 2, energy will go down by a factor of 2, and that's another power of A that you have to take into account. So you take that, plug it in here, and you have a slightly different differential equation whose solution is that A scales with the square root of time. So again, you have expansion of the universe even in radiation domination. The last case has to do with a special circumstance where the rho, the energy density, is constant. And this one is really weird, actually. So you have to have this kind of a situation where the energy density is equal to the negative pressure in whatever natural unit. So C is 1 and H bar is 1 and so on. And they both have to be constant. And what happens then, if you look here, is if rho is constant, so you move A squared to the other side, take a square root, and what you find is that A dot is something times A. And the solution of that is an exponential. So if you have a situation like this, if you have this kind of an equation of state, as we say, then the universe expands exponentially, because A here is the scale factor, and it expands, it grows exponentially with time. And this situation happens both in inflation and in this latest phase of the universe, which I didn't mention, which has to do with the dark energy. So it's a different topic. We don't need it for our purposes here. So inflation is basically, that's where this exponential growth comes from. It comes from from a very special relationship or very special behavior of the energy density. And this process is considered interesting for several reasons. It solves several problems in cosmology in a very natural way, including what's called a flatness. You can show that even if you start with a curved universe, after this huge expansion, the universe really looks flat. So you don't have to ask the question, why is the universe flat? It has to be because the inflation made it. The horizon problem has to do with the fact that the universe looks the same if you look that way and that way, in two opposite directions. And you know that, or you can calculate that for example, in the CMB, the scale on which the horizon scale at the time of the CMB should have been something like a degree, or if I remember well, on the sky. So there is no reason why two opposite directions on the sky should be correlated. Yeah. So P will be the negative piece here. So rho will be positive, but you will have negative pressure, and that's basically what drives the expansion. Okay, so the inflation basically tells us that the universe may have been all in causal contact very early on, but then this huge expansion makes it look like that the directions on opposite ends or opposite directions should be uncorrelated, but they really were correlated early on before the inflation, so that explains why the universe looks the same in all directions. And the last one is the monopole problem. So this is an issue that it is expected that magnetic monopoles were created in the early universe. We don't see them today, and one explanation is that the universe expanded so much that basically they got diluted away. Anyway, so this is a brief introduction to this process. How do you get inflation? There are multiple ways. In fact, there is this could be a whole summer school topic. But in a nutshell, one common way to do it is to suppose that there is some sort of a particle, or in field theory you would think of it as some field phi, and there will be some potential associated with that particle. Okay, V. There's a sketch of it. You can show that in field theory the energy density would scale like this. There would be a kinetic term with phi dot squared, and there would be some potential term, and there would be you could calculate the pressure as well. It's basically the same with just a minus sign in between. So now if phi dot is much smaller than V, okay, if phi dot is much smaller than V, then you can basically see that you can neglect these two terms, and rho would be effectively just V, and P would be minus V. So in that case, rho would be equal to negative pressure, roughly speaking. Also, if V is a very slow function of phi, then the energy density would be more or less constant. So then you have this situation from the previous slide where rho is equal to minus P, and they're both roughly constant, so you get the exponential expansion. And this is typically referred to as a slow roll inflation model, because the inflaton field phi would be rolling down some slope V, but it would do it very slowly because the slope of V is very, very small. And you can get into the details here and figure out exactly how slow it needs to be, and to give you the right level of expansion and so on. Okay, so in terms of gravitational waves, our general expectation is something like this. Gravitational waves were produced in the early universe along with everything else, and they decouple from the primordial plasma from the rest of the universe very early on, because gravity is a weak force. And you can get a sense of how early that is with this relatively simple arguments. So initially, of course, we're living in the quantum world then, right? So you have to think of gravitational waves as gravitons, some particles that carry gravitational interaction. And they were interacting with each other along with everything else in the very early universe. So what's the rate of the interactions of the gravitons? Well, it will look something like this. And this is basically coming from particle physics. The rate will depend on the number density of gravitons. It will depend on whatever cross-section for their interaction is. And it will depend on the speed of gravitons. The scale here, the number density will scale with the temperature to the power 3 in radiation domination. You can show that from Freedman Equation. We won't bother. The cross-section, well, we can guess that it's something like this. So, for example, if you look at particle interactions like neutrino interactions, the cross-section will look something like this. This GF here would be the Fermi constant, and then you have energy squared, and energy goes roughly as temperature in the universe. So, in radiation domination, you would replace this GF with a G, and you would have the G squared T squared. It's a guess, but it's probably a reasonable one. Without knowing more about physics of those energies, you can't really say exactly what this is, but this should be close enough. So, and then you can assume that everything is moving basically at the speed of light. So, when you plug those in, you find G squared T squared from the cross section. You have another T cubed from the energy, from the number density. So you come up with G squared T to the power 5. On the other side, how fast is the universe expanding? So from Freedman Equation in radiation domination, you can show that that's something like T squared over divided by the max with the Planck mass. And then you can compare these two. If the rate of interactions of gravitons with each other is much higher than the expansion rate of the universe, well, then basically all of these gravitons will be coupled together. They will be interacting very often. However, if the universe is expanding faster than they can interact with each other, then effectively these gravitons will be decoupled. They won't have time to reach another graviton because the universe will just push them apart faster. That make sense? So what we do then is we look at this ratio of gamma and h, the interaction rate and the Hubble expansion. And so you plug in what we had here, t to the power 5 and t squared, that gives you t cubed. The other parameters effectively just give you the max Planck mass. So this gives you t divided by the Planck mass to the power 3. And you see that if the temperature here is higher than the Planck mass, again, this is all in natural units, right? C is 1, h bar is 1, and so on. In natural units, if the temperature is higher than the Planck mass, then the rate of interactions would be of gravitons will be higher than the expansion rate of the universe, and we can basically say that the gravitons are coupled together, they're interacting together, and so they're not freely traveling. But as the temperature drops below the Planck mass, G becomes smaller than H, and at that point the gravitons become free. They start to travel freely through the universe. So at the Planck mass, which is about 10 to the 19 GeV, or about 10 to the 32 Kelvin, the gravitational waves would become decoupled. This is why this business is very interesting. It basically means that if I go back to our picture, here is 10 to the 32, if, or is it here? At this point here is where gravitational waves decouple. And you look at the time for that, that's 10 to the minus 43 seconds. So basically you're looking at right at the beginning of the universe, right after the Big Bang. And if you could measure that, you would basically be probing this kind of physics here. As I said, there are other things that go on up to 1 minute after the Big Bang, so they can change what we observe. And in that case, we would be probing different kind of physics that may be going on here. Also very interesting. All right. So I think that's it for kind of a brief introduction. Are there any questions on this so far? So we'll launch it in the inflationary models next. Yeah. You're asking if this is a good assumption. It's the best I can do with what I know. But is it correct? I have no idea, because there may be. So we're assuming here just that we're assuming here that really what matters is graviton-graviton interaction. That might not be true. I mean, we don't know the physics of that energy, right? So it gives you a flavor of what this looks like. This is probably the highest cross section that you could get. I think that's the argument. The others will probably be weaker. So that if in other words, those other ones would decouple even earlier. Okay. All right. So we'll now switch over to writing. See, we go off here. So you don't have to take notes. I'll have these posted, but I wanted to do it on the board rather than on the slides, because as I go, it paces me right. So I think it will be easier for you to follow as well as for me to explain things. So again, what we'll do is basically we'll try to look at what is the amplitude of the stochastic background due to the inflationary models. We'll focus on that because that's this earliest background that we could potentially see, and that's so the physics of it is maybe the most interesting. And then when we're done with that, I'll go back to the slides and we'll look at some of the other models as well, and we'll do that much faster. All right, so we start again with the energy density in gravitational waves. And as Joe described it yesterday, we can write this as in this particular way. So this is ln of f here, or we can write this as f divided by the critical energy density d rho gw df. So the critical energy density is the energy density needed to make the universe flat. And if you go back to the Freedman equation, you remember that there was an h squared on one side, and then there was some coefficient times rho, right? It looks something like this. This coefficient effectively is rho c, so the critical energy density. The 0 here denotes that it's the present day value of the critical energy density. The f here is the frequency, again, as observed today. And rho gw is the energy density in gravitational waves. So I guess let me give it to you now, and then we'll come back to it. So rho GW can be written as some coefficients that give you the right scale. It has to do with the Newton's constant and so on, times the expected value of the metric dotted with itself. Okay, so I guess I should be explicit here. This is a function of both position and time. So then both of these will be functions of both position and time. So we'll talk more about this. I think Joe mentioned it as well yesterday. You have to look at the perturbation metric. So this is the gravitational wave metric. You have to dot both of them. Oops, there's another dot here. So the dots denote time derivatives. So you need to take the time derivative of both of these metrics, contract them together. The expectation value of that is basically the energy density carried by gravitational waves. Where does this come from? Well, I think the best way to learn about it is the Gravitational Bible book by Misner, Thorne, and Wheeler. Okay, so it's a non-trivial result, and I'm not going to spend time on that. But we start from that. We use it. Okay, so another thing that will be very useful to us, and Joe has also done this. So we now need to figure out what this is, the perturbation metric, and that will be the critical thing that we work with, and Joe will, I'm sure, say more about that later. So what we do is this is the metric at some position in space and at some time. What we want to do is we want to think of it in terms of spectra, and Joe has already spoken about this yesterday. So we want to convert this into basically the Fourier domain. Okay, so we want to do a Fourier transform. So what does that look like? Well, here is a Fourier transform would look something like this. So instead of t, we would have f, and then we would have e to the 2 pi I f t, right? This is a Fourier transform. If I Fourier transform this, I will get this. Everybody okay with that? Yeah? Well, I can push this further because I don't need to just Fourier transform the time, right? I can also Fourier transform the position, okay? And to do that, I need to add something that looks like this, e to the 2 pi I k dot x, right? Where k now is my wave vector. But I can simplify this. So in particular, we know that k is 2 pi divided by lambda, which I can write as 2 pi f divided by c. And if I then think of k as a vector, it would be something like 2 pi f over c. Sorry, say that again. This one? I'm building up. I'm building up. So, so what I wrote down, Bruce, initially was this. Okay, without this. Okay, so now I'm building up. So the next thing that you do is you do a Fourier transform. That will look something like this. And yes, in that case, this x will become k, right? But I can change this, and instead of using the k, I can use basically the frequency, and we'll use omega hat as the unit direction vector. So this dk will effectively become the omega, and then I can combine k and k dot x and ft into one term that looks like this. If I did that right. Yes? And then the last piece is, so this is the AB here, of course, are the indices that go over time and space, but we know that the gravitational waves come in two polarizations, so I can break this into two polarization components. So instead of that, I can write HA and have a unit tensor that looks like this. and then I have to sum over the polarizations, and there are two of them. And another thing that's important, I guess, so instead of k, I can write here omega hat, and I should just make it clear that the polarization will depend on the direction of the gravitational wave. So this is, Joe has written this before, but I wanted to go through it one more time because first, I'm sure he'll need it again. And we all had to go through this many times to really understand what this means. This is a plane wave decomposition of the strain of the gravitational wave metric, and you can see that it basically has some amplitude HA, which is a function of frequency and the direction of where the gravitational wave is coming from. And then you have the wave piece, okay, and you have the unit tensors in the tensor decomposition, so the plus and the cross. Yeah. You could do that. I didn't in my notes. I think it's your choice how you want to define it, but you could do that. Okay, so we will need expansions of this kind again. So the intuition, what I hope you will carry from this is that whenever you have something like this, you can write it in terms of the Fourier transformation, but that transformation does not need to be limited to just time and frequency. You can also do it in space, in which case the wave vectors come in, and you can also decompose in terms of the polarizations. All right. So you can then take, as an example, you can then take omega gravitational waves, and I'm not going to go through this calculation, but just to highlight it. Actually, I'll leave that. I think that's already Joe's territory. It's in the notes, so you can look at it there. But effectively, you can use this with some assumption about the cross correlation of different amplitudes, and Joe has described that yesterday as well. And then you can derive a relationship between the energy density and the strain power. Yeah. That's an exercise. Excellent. All right, so now you have another motivation to do that. All right, so at this point I'll start talking a little bit about the inflationary model. And to do that, we need to deal with basically quantum mechanics and even quantum field theory. So I'm not going to assume that everybody is familiar with quantum field theory. I'll be kind of walking on a knife edge, and if you ask the right question, I'll fall off. You can take it as a challenge, but please be gentle. All right. So to give you an intuition, so what we're going to do is we're going to look at, we're going to think of the universe early on as having these vacuum fluctuations. So we'll think of modes or oscillations, if you like, in the gravitational wave field. And we'll try to see or figure out what happens to them as the universe expands. Okay? So to do that, it actually is very helpful to go through a simple kind of a toy model where you just think of a simple pendulum. Okay, so simple pendulum in quantum mechanics is the quantum harmonic oscillator. So I'll just remind you, we'll have a pendulum like so with some length L, and we know that it's of course the frequency would look something like this, where G is the Earth's gravitational constant, 9.8. And we know that so to remind you, we can write we can define the raising and lowering operators in this particular way. So n and n plus 1 are states, eigenstates of the quantum harmonic oscillator. Okay. So I hope everybody has seen things like this before. Otherwise, this is going to be very hard. And then we can define the the number operator, which is a dagger a, and we know that n acting on some state n will just give me the number of particles I have in that state. Okay, and we also have, so this would be a dagger a acting on n. But if I reverse them, if I do a dagger acting on n, that will give me n plus 1 times the state n. Okay, this is just a brief reminder of the quantum harmonic oscillator. So we know that these states, the state n, we can write it in coordinate space as some coefficient times the exponential that maybe looks something like this, and then we have the Hermite polynomial. Okay, this is supposed to be an alpha, and the energy level corresponding to that will be h bar times omega times n plus 1/2. So that's the these are the eigenstates of the quantum harmonic oscillator Hamiltonian, and we can also think of them in terms of the raising and lowering or creation and annihilation operators. And I'm mentioning all of this because we'll need it. So suppose that we start with some initial length Li. Okay, this alpha here, let me also write it, that is dependent on the mass omega and, well, h bar. Okay, so let's suppose we start with some initial L sub I. Okay, so then that will give me initial frequency, and I will have initial frequency here, so alpha I. This will be initial, this will be initial as well. Okay, so these will be the initial some initial set of states and energies. So let's consider the ground state when n is equal to 0. So that we can write as, turns out it's a square root of alpha I divided by root pi. We don't care about those. So it will look something like this. And the energy level initially would be E0 initial, which is just h bar omega I. Oh, sorry, divided by 2. Okay, so we're thinking of this pendulum. It's in the ground state, and it has some initial length Li. Then we're going to extend this length of the pendulum to some final length Lf. Okay. Now, if I extend, so you may ask, how do you do this? Well, let's pretend that nature has a switch that if I turn it, it just doubles the length. Okay, it stretches the space. Okay, and of course, this is what happens with gravitational waves, the stretching and so on. So it's relevant for us. But for now, let's forget about how this happened. Let's ignore that. Let's suppose that we somehow increase the length. Now, if that increase happens very slowly, so if so we go from Li to Lf over some time t. Okay. If that time is much longer than the period of the oscillation, okay, then at each point in time the pendulum will keep doing its thing, right? It will basically be imperturbed, and when you get to this bottom, you will still be in the ground state of the quantum harmonic oscillator, but for this new length. Okay, so if t is much longer than the period, which is the inverse of the frequency, then the original initial ground state goes into the final ground state. Okay, so the system slowly morphs into the ground state of the long pendulum. However, if I do this very quickly, right? If t is much smaller than the period of the oscillations, then what I will find myself in, this bob, will be in the same state it was when I started. But now I'm in a different system, and my my eigenstates are different than what I started with. Okay, so now I have, this is a seriously different situation, and I have to treat it carefully. Okay, so in the final state, in the final configuration, I should say, in the final configuration, we'll have some psi n f of x, which will go as e to the minus alpha final squared, x squared divided by 2, and then we'll have the Hermite polynomials that look like this. The alpha f here will be now square root of m omega final divided by h bar, and the energy levels will be again related to the omega final. And omega final is the square root of g divided by L final. So what the situation I'm in then is, if I quickly change the length of this pendulum, the state of the pendulum will be the same that I started with, which is this one here. But now I have to think of that state as a superposition of these eigenstates, because these are the new eigenstates of the system. So I can write the initial wave function as a superposition of these eigenstates. So I'll have psi n f of x and some coefficients c sub n, multiplying them, and then n goes from 0 to infinity. And these coefficients, we know how to calculate them in quantum mechanics. That's the integral of psi 0 initial dagger times the psi final, right? Okay, so these coefficients can be calculated. I know what psi and final are. Here they are given by this expression. Well, I know the initial state was a ground state of the initial potential, so I can compute this. Okay, I'm not going to do it on the board, but it's at least possible. And then you can ask, well, what is the energy level of this state? Okay, the energy level is psi 0 initial dagger times the Hamiltonian operator times psi 0 initial, right? And this is integrated over all x. Again, from minus infinity to infinity. Okay, so I can expand each psi 0 dagger and psi 0. I can expand it in terms of the these guys, the new eigenstates, and that you can show that that's just equal to the sum of Cn squares E sub n's final. Okay, so you can see how that's going to happen. And when I take this and plug it in here, H acting on these will just give me E sub n, right? So H acting on psi n final will give me E n final. And I'll have one Cn coming from this wave function, one coming from the dagger, so I'll get the Cn squared. Okay.
So this is the analysis when we're doing the length change.
Yes, quickly. So that's good. I know that. Now what I can do is plug in the Cn's, which I can compute here. I can plug them in here, okay? And what I can find is that this ends up being h bar omega final times omega initial minus omega final squared divided by 4 omega initial omega final plus a half. And that's to be compared with do I have those, or did I erase them already? Here. So remember, I started with a ground state initially, which meant I had h bar omega times 1/2, but now I have this term. So what that tells me is that the number of particles, n, is this term here, omega initial minus omega final squared divided by 4 omega initial omega final. And when I take the L to go to infinity, right, when I'm expanding it a lot, then omega initial will be much bigger than omega final. And so I can forget about this. This becomes omega I squared. It cancels one omega initial in the denominator. And I get omega initial divided by 4 omega final. So what just happened? I had 0 occupancy level initially, right? N was 0 here. But when I make this change real fast, I end up having vacuum modes in this number. Okay? Again, omega is bigger, omega initial is bigger than omega final. So this number, in principle, could be much larger than 1, depending on how much I expand it, right? So that's the upshot of this, is that if you somehow increase the length of the oscillator quickly, then, and by quickly we mean faster than over a shorter period of time than the period of oscillation, then you quantum mechanically create additional vacuum modes. Okay, and that's something that we will be seeing again. What we will do next is we will think of the gravitational waves as a collection of oscillators, and each one of those will be doing something like this. Okay, so we'll combine all of those effects and hopefully get a spectrum at the end of the day. Everybody okay? Any questions? All right. All right, so so how do we do this? All right, so let's suppose, what I do here is basically following the majority review paper that I mentioned early on. So you can find basically all of the steps there, I may fill in some of the details and so on. So we work in natural units, so h bar and c are 1 and so on. And we will work with the conformal time, which don't worry too much about this, but really what it means is that we'll define it as eta. What it means is that we take the regular time and divide it by the scale factor a. And in that kind of with that kind of units, the metric can then be written as the scale factor a of which we can, I guess, write as a function of the conformal time as well, squared, times the Minkowski metric, mu nu, plus the perturbation, which we'll write as h mu nu. Okay, so that will be the h here would be our gravitational waves. Now the and this here again is the Minkowski metric, so it's -1, 1, 1, 1. All right, so then the perturbation h mu nu, or we can switch to the transverse traceless gauge. I trust you have seen this a couple weeks ago, right? So I don't have to talk about that. So the perturbation then can be written, or we can expand it again. Here's another way of another case where we do the expansion. Let me write it all out, and we can then talk about it or stare at it. So we'll write it in this way. So we'll write this as phi, which will be a function of the direction k, and it will depend on time, and it will depend on the polarization. Then the space piece will be the wave, k dot x, and then we have to add the tensor, or the unit tensors. And here, just to be explicit, this would be a function of the position and time eta. Okay, so what did I just do? Well, this is, you can think of it as another Fourier transform or Fourier decomposition. This is this decomposition here is the decomposition in two polarizations, right? So A is plus and cross again, so no issue there, I hope. The rest here is taking this metric and decomposing it into plane waves in space, okay, k dot x. But the time dependence here is potentially more complicated. It's not just a simple wave anymore, because now we have the expansion, okay? So this phi will be the amplitudes, but the amplitudes will depend on time in a most likely more complicated way than just simple oscillations. All right, so that's what we're starting with. So we need to study these phis, and these, if you can basically already see that these phis are effectively the oscillators that we care for, because each of those is an oscillator associated with some wave vector k. Mind you, we could also write this sum over k as an integral. Okay, there's really, as far as I can tell, there is no reason not to, but that's what Majora does, so I'll stick with it. The other thing that I should mention is that when we think of the position and time here, these are what we call the comoving coordinates. So x here would be comoving coordinates, which means that if I wanted to find the physical coordinates, I would have to multiply by the scale factor a. And similarly, if I wanted to know the physical wave vector, I would have to divide by a. Okay. So comoving coordinates are the coordinates that are basically expanding with the universe. So relative to that reference frame, we have the coordinate x, but the physical coordinates, you have to take out the scale factor. All right.
Do I remember that? Sorry.
Yeah.
Remember that in comoving coordinates, as things expand, that does not change.
Yes. Yeah. That's the idea. So so how do we deal with this? Well, we now need to think about what governs the behavior of the phi. And remember, phi is basically our perturbations. It's basically the metric. What equation governs this? Well, it's Einstein's equation, right? Einstein's equation, when you look in this weak field regime, boils down to a wave equation. But in this case, the metric might not be flat, right? The underlying metric might not be flat. So you can show, and this is something that you can get from the Creighton and Anderson books. You can show that this is true. So if you have some sort of an underlying metric, G0, let's say mu nu, this is true. These are the covariant derivatives in this original underlying metric. And this is the perturbation. Let's forget about that. So if we were dealing with the flat underlying metric, right, then this would just boil down to the square operator, right? This will become a wave equation. Okay. So now what you would do is remember, this is a function of position and conformal time. Now you can take this, right, and expand, plug it in here. Okay. Remember that these deltas or nablas, I should say. So let's say the new one looks something like this. There is a derivative. So d dx nu minus, these are the Christoffel coefficients. So this would be nu a. Let's put in an h a b here. So here would be h a b, and then this would be h. Let's see. Sorry about that. Gamma b. There was was in one more term. Okay, it looks something like this, right? So it's a nasty thing, as usual. And so you would have this for the one of these covariant derivatives, similar thing for the other one. And then you see that you will have first a simple derivative of the perturbation relative to nu, and then another one relative to mu. Then you contract them and you get basically the square operator. So those this term from these two covariant derivatives will give you two time derivatives, the second time derivative and the second position derivative. When you apply those here, you see that the two time derivatives will just give you phi double dot, right? And two spatial derivatives will give you k squared. So what you end up with, I'll just give you the answer, is an equation that looks like this. So you have phi. Let's denote the derivatives relative to conformal time with primes, okay? And these are labeled by k wave vector. Then there is another term, 2a prime divided by a times phi prime. And then the last one is k squared phi, and that's equal to 0. So what I was trying to explain is this term and its corresponding term from the mu covariant derivative will give you two time derivatives and two spatial derivatives. Two time derivatives act on phi, so they just give us phi double prime. Two spatial derivatives give us k squared. So that's this piece. This one is harder to see. I don't want to spend time on it. You can look at the notes, and it's almost magical that it happens to be this simple. Yeah.
Should there be a minus k squared? I mean,
Minus k squared.
The wave equation, if you ignore
You know, I have a plus here, and I think it is a plus,
okay.
but I'm not a.
Okay.
Yeah.
Okay. Sorry.
That's right, I think, yeah.
Okay, sorry.
Okay. So, so remember A and B just run over the spatial piece, right? So that's the wave piece of the metric in the transverse traceless gauge. So we start basically with this, and it turns out convenient to simplify the equation. It turns out to be convenient to rename to write psi to be a phi. Okay, so both of these will have indices k, and when you do that, the equation boils down to psi double dot k or double prime k plus k squared minus a double prime over a psi k equals 0. So this is really the equation we were after. Okay, so this is now telling us how each of these oscillators behaves over time. Okay. Any questions so far? This one here? Yeah. Is it assuming the Lorentz gauge? I believe that's true. I believe that's true. I'm not, it's been a while, so I can't remember exactly, but I think that's true. There is a derivation of this in the Creighton and Anderson textbook. So you can, I'm sure, find the details there, or we can discuss afterwards. Okay, so that's the piece we need. So our next next step then is let's imagine that we have two phases, phase 1 and phase 2, and these will be something like inflation and radiation domination, the two phases that follow each other, or you could have radiation domination and matter domination, and also two phases that follow each other. Or there could be additional phases that we don't know of. So you can postulate your own universe, something else that happens in the early universe, and you can have another phase transition. Yeah. I have it as a double derivative. It will come basically from this double derivative hitting A twice. Yeah. What do you mean by we don't have vacuum? Yeah. So yeah. No. So you're absolutely right. So you're questioning whether this equation can be coupled with with this kind of an expansion. Yeah. Yeah. So I believe the way out of that is to look at which modes are relevant. And if you do it carefully, which we can't do, it turns out to be okay. There is a discussion of this in Creighton and Anderson as well. It is a little bit tricky. You have to follow. Basically, you try. What we will see is that only certain modes will get amplified, and for those modes, this equation turns out to be okay. Yeah. So, but in the end, what we yeah. So in the end, what we will care for is the transition piece, and in the transition, the ones that will be relevant are the basically the modes that are on the horizons. The relevant scale will be the horizon scale at the time of the transition, and we will the argument is that for that energy scale and that that wavelength scale, these equations will be okay. So we can discuss more, but I think that's the answer. Yeah. Yes. We're not coupling them back to the T. Yes, absolutely. That's right. Yeah, that's correct. Okay. All right. So all right. So let's suppose now we have two regimes, 1 and 2. So regime 1 we'll write down the metric in terms of this expansion, and we will write down a similar thing for the phase 2, and those two will be will there be a transition from one to the other or some time scale, we'll call that capital T. So in phase 1, the solutions of this equation here we'll call the solutions F and F. Yeah, we'll have solutions F sub k. In phase 2, we'll just label those with a capital F. And in this case, we'll have HAB, which is now a function of, remember, the conformal time and the position. We'll now expand it so there is a square root of 8 pi g out front. We'll have sum over the depolarization, and we'll have the integral or the sum over the wave vector. So this would be the proper normalization here. So we will have, there will be 1 over a of eta because of this definition here. Okay, there's another factor of a so that we have to account for. And then we have the actual amplitude. So we'll write this as the lowering operator, okay, times the amplitude solution f, k, which is a function of eta. And then we have the spatial piece. And then we have to add the dagger of this. So we have the creation operator, a dagger, f star, which is a function of eta, e to the minus I k dot x. And then we have to add the tensors. Okay, so this is a very similar expansion to what we did before, but now we're thinking of this in quantum mechanical terms. So this is really field theory. We're making a field theoretic expansion of this quantity HAB. If you ignore the raising and lowering operators, this is exactly what we had before classically. We're now adding the raising and lowering operators, and that changes a little bit the normalization, but the expansion is effectively the same as before. So again, we're thinking of each of these FKs as an oscillator, and we're adding the raising and lowering operator for each one of them. And of course here the A plus, let's say, of K, if it acts on the vacuum in the initial phase, it will give me just 0, right? It will lower the vacuum state, so that's not possible. And the same thing will happen if I take a cross and act on the vacuum state from the phase 1. And you can write the same thing for this, right? For the second phase, you can write exactly the same thing, but you will have to you will have different raising and lowering operators now associated with the Hamiltonian in the second phase, and you will have, instead of small f's, you will have the capital F. So maybe I should write it out. So this would be in phase 1, this would be in phase 2. So the same 8 pi g square root sum over a's integral over the k and then this becomes, so now we have to change the raising and lowering operators. In the notes I use just the capital, so capital A now is my lowering operator in phase 2, and it's a terrible notation because I also have capital A as the let's change that into B's, right? Saves us some confusion. And then we have this is multiplying the amplitude F. That's the solution of that differential equation in phase 2, which is labeled by the k's, and we have e to the I k dot x, and then plus the dagger of this. So we have a b dagger F star, oops, and I think that's it. This is a B. Okay, so these are my expansions. So the F's again are the solutions to this equation. Okay, so I know how each of these modes behaves as a function of time. Okay, each of the spatial modes labeled by the k's, how it changes over time. I've added the raising and lowering operators to think of them in terms of quantum mechanics, because we need that transition to look at the occupancies levels, right? And I can do this in phase 1, I can do that in phase 2, and I have expansions that basically look the same. Okay? So then the question for us will be, how do I relate these two when the transition happens, right? That's the tricky part. Now the little f's and the big F's, they are complete sets of functions. They're basically the bases of the function space, or in each of their relative phases. Which means that I can express little f's in terms of big F's, right? Because these are both you can think of both of them as bases of functions. So I can write something like this: f sub k. We can write this as a sum over some k prime now of coefficients alpha k k prime. Okay, so this alpha now is a coefficient that's labeled by both k and k prime vectors. Okay, we could again think of this as an integral, but majority doesn't, so let's stick with it. And then we multiply this by the phase 1 coefficient, so fk and the corresponding ik prime now dotted with x. Okay, and then you have to add the conjugates. So we have another coefficient, we'll call that beta kk prime, and we have f star now, which is labeled by, sorry, this is labeled by k prime, and e to the minus I k prime dot x. So these ones, the alphas and betas, these are called the Bogolyubov, coefficients. Yes.
Wouldn't you want to express things in terms of big F, because that came afterwards? Those would be the modes that we would observe today.
You mean writing little f in terms of the big F's?
Yeah.
You could do that. It's equivalent. In the end, what we want is these alphas in the end. And we will have to relate them to the present day frequencies in the end as well. So whatever you do, it will lead to the same answer in the end. But my goal here is to take this and plug it in here, and then compare with this, and that will give me a connection between the little a's and the big a's.
And you're going to do that at this eta that's the boundary between the two phases?
Correct. Yes. Yes. Mm-hmm. Yeah. So that's exactly right. Yeah. So when you so it's in here, right? So the A changes, the time dependence of the scale factor in the two phases will be different. Okay, so it's this piece that will be different in the two phases, and that will lead to this different solutions. Basically, yes, that's basically it. Now, if you think about it, that's exactly the same as what we did with the pendulum. We had a quantum harmonic oscillator short and long, and I said the change happens quickly. So the initial state, which was the ground state of the short pendulum, was then expanded as a superposition of eigenstates of the long pendulum. That's what we're going to do here. So we'll have these are basically solutions of the short pendulum for let's say in the inflation phase, and then we'll have the long pendulum in the radiation dominated phase, which will give us different A double dot or A. We'll have a different set of functions that describe the world, the system at that time, and we will expand one in terms of the other. Yes. Mm-hmm. Yeah. So, yes. To the curvature. Correct. Yes. That's what I was referring to when in your earlier question. You have to worry about this equation, and its applicability depends on the size of the mode that you're looking at. And it turns out that for the modes that we will be expanding or amplifying, it is okay. I guess that was your comment. Okay, seem to know more about this than I do. Okay, thank you. All right, so let's see, we have 10 minutes. So I'll switch to the slides really quickly because I don't want to write things. So remember we have, where we ended is we expanded the perturbation in phase 1 and in phase 2 with these coefficients little f's and big F's. And we wrote down this connection between them in terms of these coefficients, which are called the Bogolyubov coefficients. So then what I will do is I will take the Bogolyubov expansion and I will insert it here, okay? So you can see that in this first or second line, this is the lowering operator in the second phase, so that's this guy. And instead of the capital F, we write down this expansion, so that's this nasty thing here. And then the second term is the conjugate of that. Then this is not terribly difficult, but what you do basically is you combine the terms that go with k dot x and with minus k dot x, right? So the k dot x terms are this one, and you have those two terms here, and the other two terms go back here. And then you want to compare with this, right? With this first line. You see that here, well, first of all, this is the integral here is over k's, and the sum is over k primes. So you basically swap the k and k prime. You can do that because they're both just dummy variables. And then you can reorder the summing and the integration. And what that allows you to do is basically basically the k prime becomes k here, and so the k primes and k reverse everywhere except in the summation and the integration here. So in the end, you have an expression that looks like this. Okay, so you have something multiplying little f I k dot x, and that's exactly what you have here. So you have something multiplying little f I k dot x. So this whole thing here, okay, then is my lowering operator in phase 1. So effectively what I've done is I've used this expansion to relate the lowering operator in phase 1 to lowering and raising operators in phase 2 using the appropriate coefficients. Is that okay? Let's see, maybe I should write this down. Sorry, say that one more time.
So I can move the sum over k prime in your notation all the way into inside.
Yes, you could put it in here, yeah. Yeah, so that's actually, let me write those down because I think we'll need them in a second. Okay, so we can write little a, the lowering operator in phase 1, we can write it as a summation over k prime of the lowering operator. Let's just change this a into b here. Thank you. Okay, we have a, b, which is a function of k prime now. E to the, alpha k, k prime k. And then we have the second term, which is the raising operator. Also a function of k prime. And then we have the coefficient beta k prime k, which is starred. Okay, and then the you can do a similar thing going the other way. So you can relate the phase 2 operators in terms of phase 1 operators. So that will look something like this. Okay, kk prime minus the dagger and beta, I think it's just beta. Okay, so we start with that. I guess we don't need a slide anymore. And we'll make, let's see, basically out of time. So we'll make one more argument, which is, so what we've done so far is basically fairly general. You can deal with things even if the transitions are not homogeneous and isotropic and so on. This would still hold, but we will assume things to be simpler. We will assume that the transition, the metric and the transition are both isotropic and homogeneous. So the metric is homogeneous, isotropic. Okay, so that's an assumption. And what that means is basically we don't need to worry about the directionality of this vector k. We need to only worry about its size, its amplitude, and its amplitude really is just the frequency. Okay, so we can simplify things very much. So we can basically say that alpha k prime will be we can write it just simply as a function of the frequency, and the k and k prime would have to be equal. Okay, and similarly for the beta, we'll have beta as a function of frequency, and again the delta in the k's. Okay, so with that change, this will simplify quite a bit. So this implies that, let's say, the lowering operator in the phase 2 can be written as a sum of over k primes, a of k prime times alpha f delta kk prime, okay, plus the dagger of that, or the conjugate of that. Let's see, so that's actually a minus sign, right? So minus a dagger of k prime beta f, and then the delta function in k prime. And it's a star here. Okay, and so if frequency is the only thing that matters, we can also remove the dependence of k on frequency, and let's drop the dependence on the just to keep things even simpler. Let's drop the dependence on the polarization as well. So we're assuming that there is no difference in polarizations. So then we can write A sub f. Okay, so now instead of having the k dependence, I'm replacing it with just dependence on frequency. That becomes equal to just A sub f. So this is now a lowering operator in phase 1, which is only frequency dependent, times alpha sub f. And similarly, minus A dagger. Sorry, I had I think I messed up with the stars. There was a star here and a star here and a star here. Okay, minus A dagger f times beta f star. Okay, so we have we basically have gotten to the point where, assuming the homogeneity and isotropy, we can relate the raising and lowering operators in phase 2 to the raising and lowering operators in phase 1, and we don't need to worry about the directionality anymore based on these assumptions. So the only thing that matters here now is just the frequency, which is the amplitude of k. Okay, I think we should stop here. Let me ask if there are any questions. Yes. You mean here? Let's see. So I have them on both terms, but let me double check this because I suspect it's a typo. So this one is probably a suspect. Anything else? Okay, that's that.